I better shout. Okay, my name is John Worrell, and I'm Professor of Positive Science here at the LSE, and it's my pleasure to be chairing this session and to welcome you all here to the LSE. I'm very sorry that we finished up in a room that's nowhere near big enough. We got the lucky few, there are two video rooms elsewhere, not very satisfactory, but still. It's my special pleasure to be introducing our speaker this evening, Lawrence Krauss, who is a cosmologist of world renown. He got his PhD from MIT, he's taught at Yale, Case Western Reserve University, now at the Arizona State University. He has sold the wonderful source of reliable information. Wikipedia tells me authored or co-authored more than 300 science articles, and was one of the first physicists to take seriously the possibility that a large part of the preponderance of the energy in the universe is contained in empty space, so-called dark energy, which has continued to be empirically predictively successful since then. He's also very well known as a public intellectual, as Scientific American called him. He gives many lectures like this. He's written many books that explain the wonders of science to the educated layman, and he's won prizes because of his work. He also served as scientific advisor to the Obama presidential campaign. So it's a great pleasure to be welcoming him. He's recently published a book, as most of you will know, called A Universe from Nothing, Why There's Something Rather Than Nothing, and it's on that theme that he'll be talking this evening. So with apologies to him in particular for all the hold-ups and the building work and the room not being big enough, let me introduce Lawrence Krauss.
Okay, good. I need to sit over there. I apologize to, especially to the people, I don't even know where the camera is, who are in the many video rooms. I just ran over there to say hello to them. I don't know if they can hear me because there's no interactive link, but you can please know there are more people watching this on video than live, which I find disgusting. But in any case, such is life. I hope you'll all complain to the LSE events people, who obviously are humanities majors and don't realize the interest in science. Thank you for coming, and I appreciate being here, and I'm trying to calm down, but I will at some point during the lecture do that, presumably. I have lectured, I find myself often on YouTube, so I want to try and, many of you may have seen a lecture I gave on this subject, and I want to try and be a little bit different than that lecture, so that it's new. I try and have different lectures each time I lecture, but that means there'll be some material that I won't cover, introductory material perhaps, but of course the good news is it's all in the book. Okay, well I showed a bunch of things at the beginning so you'd have something to read while I was being introduced, which is generally my policy. And I run a program at Arizona State University called the Origins Project, and it's called that because origins are by far the most interesting thing. They're the forefront of all fields, wondering how we got there. And what I want to do today is first set the stage for the mystery that I want to talk about, and then I will discuss it. So first I want to put us all on the same wavelength and describe to you the real crazy universe in which we live. This is it. I was just saying to students the other day at the New College Humanities where I'm lecturing that people in London may not know this, but these are stars, and Arizona we see them. But this is the beautiful night sky, and the amazing thing about this picture is, as beautiful as it would be should you go out in the country and actually see these things, is that the really important stuff is the stuff you can't see, the stuff between the stars, and it's changed completely our understanding of both the past and the present, and as I'll describe, the future. So the question You have something to tell me? The video link can't hear very well. Can you speak into the mic a bit more? Which mic? This mic or that one? You sure? I suspect it's this one. In which case, they're, as we say, something out of luck where I come from. I will try and speak loudly, but I'm not going to tether myself to that mic. So, I don't know if you have a technician that can come in and arrange the mic, this mic to actually project through there. So you'll come and tell me. You'll take the 10-minute walk over there and come back. Okay. Well, this is already funny. In any case, the question that I want to address is a question that's been around as long as people have been asking questions. It's a question that's become a profoundly, well, I hate to apply the word profound to it, a very significant religious question. The question, why is there something rather than nothing? It is generally, in some sense, the last bastion of those who would like to find a place for God. Now that we've dispensed from Him in human evolution, the one question is, how can you get 100 billion galaxies, each containing 100 billion stars, out of nothing? And that certainly seems to require some kind of supernatural shenanigans. And so, one way to answer that question is really quite simple. You just write a book and it begins this way in the beginning. It doesn't explain anything about anything, but it satisfies some people. But the actual way to do it is not to assume the answer before you know the questions. And so instead I want to turn back to the real universe and try and use the universe as a guide, which is what science is all about. And I would argue, in fact, that the interesting question is not this one, and I've been debating it a lot with philosophers lately, and some theologians, although I try not to talk to theologians. Why questions are not really interesting questions? Why questions really don't make sense? Because they presume purpose. If any of you have children, you will know that why questions can become annoying. Eventually, the only answer is because. Because they serve purpose in the universe, in fact, or purpose to whatever. An example that I haven't given in the book, although actually I'm giving it in the paperback version of this because I've had to deal with this question a lot, is as a cosmological example, which is from Kepler, who asked the question, why are there 6 planets? And he thought he had, and for him it was a real question because he thought it would reveal the mind of God. And he had a good answer. He said that there are 5 platonic solids. And around each solid you can inscribe each of these solids in a sphere, and then those spheres would separate 6 planets, and since God was a mathematician, everything seemed to work out fine. He understood the mind of God. Now, the problem with that, of course, is we know there are not 6 planets. There are 9 planets. And there are 9 planets. Pluto will always be a planet for me. My daughter did a project on Pluto when she was in her 4th grade, and I certainly don't intend for her to go back. But if you discovered which one of these is not, are you going to tell me?
They're all working now. They're
all working now? Yeah. Okay. So if you're in the other room and you can hear me shout, we won't hear you, but it'll make you feel better. In any case, where was I? Yes, so there are not 6 planets, there are 9 planets, but we know that the question, why are there 9 planets, of course, is not an interesting question, because we know that our solar system is one of many solar systems, and many of which have different numbers of planets. What we really want to know is, are we unique, are we distinguishable, and could there be life elsewhere? And so why questions are generally not interesting, which is why philosophers spend most of their life talking about it. So anyway, I want to use the real universe and come back to this picture. And the real universe has changed a lot. The first thing I want to remind people of is that in a single human lifetime ago, our picture of the universe was quite different than it was now. 85 years ago or so, 87 years, the universe was both static and eternal. Conventional scientific wisdom suggested the universe was static and eternal, and it contained one galaxy, our own, the Milky Way galaxy. We now know that there are over 100 billion galaxies out there in the universe, so things have changed tremendously. We are like the early map makers. And it's not too surprising that we are surprised. And we are surprised, and it's that surprise that I want to relate to you. I won't go into the discovery of the expansion of the universe, but since this is the London School of Economics, which I assume means that many people here are training to become lawyers, I wanted to present this slide because it does give me hope for humanity. Because this is the person who convinced the world that the universe was expanding, Edwin Hubble, by observations I wish I had time to talk about. But for me, the most important thing about Edwin Hubble is that he began life as a lawyer and then became an astronomer. So there is hope. We're all in any case, he discovered that the universe is expanding, which changed everything from a philosophical and scientific perspective. In particular, it told us the universe had a beginning. And that was very different. And of course, if it had a beginning, and that beginning we now know is 13.7 billion years ago, except in Arkansas and Ohio and a few other states. If it had a beginning, the big question is how will it end? And that became the central question of 20th century cosmology. Now, it turned out Einstein was ultimately able to, actually, even before the fact, was able to explain the expansion of the universe, although he didn't know he could. But Einstein's general theory of relativity tells us that space is actually curved in the presence of matter. Space responds to mass. And these pictures are to guide the eye because I can't draw curved three-dimensional universes. We are three-dimensional beings. We can't picture them. I can't picture them. You can't picture them. I can write them down mathematically, but I can't picture them. So I draw these guides to the eye. But it turns out that indeed, even for a curved three-dimensional universe, there are just three types of geometry: an open, closed, or flat. And these are the two-dimensional analogs. And a closed universe I might not be able to picture, but I can certainly describe. In a closed universe, I wish I knew where the camera was so I could stare at the people out there, but I don't know where it is. Anyway, if I stare along, if I look far enough in that direction in a closed universe, I see the back of my head. Okay? Light will actually travel around a closed universe, etc. But the important thing is, in a universe dominated by matter, a closed universe will expand and stop and then recontract in a big crunch, the reverse of the Big Bang, whereas an open universe will expand forever, and a flat universe will just be the boundary between the two. And the big question is, which universe did we live in? And that's, by the way, the reason that I got into cosmology, in fact, as a particle physicist, because I wanted to be the first person to know how the universe would end. It seemed like a good idea at the time. Now, the great question is, which universe do we live in? But since mass curves space, that means you just have to weigh the universe. And that was the simple prospect. So, I want to tell you in a few minutes how we have, in fact, weighed the universe. And I want to do a little bit of history, since I like history. And I want to take you back to a kinder, gentler time, 1936, which maybe wasn't a kinder, gentler time, but it was for science anyway. And the magazine Science, which is a distinguished, and still was, a distinguished scientific journal then, published an article that had the title, "Lens-like action of a star by the deviation of light in a gravitational field." Now, for those of you who may be aspiring scientists and want to publish one day, or particularly get rejected by the journal Science, here's how this article began. Some time ago, R.W. Mendel paid me a visit and asked me to publish the results of a little calculation which I had made at his request. This note complies with his wish. Try that now, okay? You can get accepted. Now, the author had credentials, it's true. His name is Albert Einstein. But what he published was a calculation that he thought was entirely unimportant. He realized, in fact, the discovery that made him famous for the world was the realization that space is curved and light curves in curved space. But he realized that this could mean that space itself could act like a lens. If I had a source of light and a big mass, then if I have a big enough mass, the light can go around the mass and curve and come back and be focused again and be magnified, like my glasses magnify things. Or if I had a cut glass goblet, which I don't have, and I look through it, I see many versions of you. And space could do exactly the same thing. But he said it would never be observable. He found it was unimportant, in fact, and this was the calculation which Mr. Mendel convinced him to perform, and he actually had thought it was so important that if you go back to his notebooks in 1912, well before he finished general relativity, he did exactly the same calculation. He just forgot he'd done it. So he published it, and then one of my favorite things is if you read the correspondence with the editor, you will read a note from him afterwards. Let me thank you for your cooperation with the little publication which Mr. Mandel squeezed out of me. It is a little value, but it makes the poor guy happy. And that's how science is done. Well, he was completely wrong. It wasn't a little value. It allows us to weigh the universe. And in fact, in this picture, this is precisely the phenomena that Einstein said we'd never observe. This is, in fact, an example of what we call gravitational lensing. This image is a Hubble Space Telescope picture, one of my favorites, but they're all one of my favorites. It's an interesting picture. It's a deep space picture. In fact, every object, every spot in this picture is a galaxy, not a star. And each of these galaxies contains hundreds of billions of stars, and this is a cluster of galaxies. Clusters of galaxies are the biggest bound objects in the universe. There's nothing bigger. So anything that can fall into anything will fall into a cluster of galaxies. I'm trying to stay over here because I realize these microphones may be all they can hear over there. These are about 10 million light years across. It takes light 10 million years to cross from there. This particular cluster is 5 billion light years away. 5 billion light years away. So that means the light left these stars before our sun and Earth formed. 4.5 billion years ago. And that also means, in the 5 billion years to get to us, that most of these stars are no longer around. They've died. And the civilizations that may have existed around them have died with them, unknown and unheralded, as ours will one day. But you don't have to be a rocket scientist to see that there are these weird blue things. And these blue things are images of a single galaxy located 5 billion light years behind that cluster. 10 billion light years away. It would not be visible, but it's magnified by the mass here, which acts as a lens and also split. All of these images are images of exactly the same object. Remarkable, telling us that indeed space is curved, as we knew, verifying that if anyone mattered, if it mattered to anyone. But now you see the point is we understand general relativity, so we can work backwards. We can use this to weigh this system. We can ask how much mass is there in the system and where is it distributed in order to produce this image. So we do that. It's a complicated thing called a mathematical inversion, but we can do it. And this is the image. This is where the mass in the system are. These are the spikes are where the galaxies are. But what you notice is the huge mountain of mass where the galaxies aren't. There's 40 times as much mass in this system as can be accounted for by all the stars and hot gas in all those galaxies. 40 times as much mass. It doesn't shine. And physicists, with their incredible linguistic perspicacity, call this dark matter because it doesn't shine. And there is 40 times as much dark matter in this system as visible matter. And what makes that incredibly exciting, for particle physicists in particular, is that we know from different arguments that there can't be enough protons and neutrons, the stuff that makes up normal matter. There aren't that many in the universe, by a factor of almost 10. They can't make up the dark matter. So the dark matter must be made of something else. Some new type of elementary particle, something that interacts so weakly it doesn't shine. And that makes it very exciting because you see, that means it's not just out there. It's in this room, going right through your bodies as you nod off during this lecture, particularly in this video room. Because you can't hear it. But that means it's exciting because we don't have to look out there for it. We can look for it here. We don't have to do it here. In fact, we look for it deep underground. Because, can they hear? Anyone know? Yeah, they can. Oh, good. Hi. So we can look for it deep underground, and in fact, we can build detectors. I think I think I have one here. Yeah, which actually one of which these detectors I proposed a quarter of a century ago. Deep underground, because above ground, cosmic rays are bombarding the Earth, and these particles interact so weakly, most of them go right through the Earth without knowing it was there. And so we go in deep mines, and this happens to be a boule of germanium, the stuff that makes a computer. And you just have to cool it down a little bit above absolute zero, and then every day billions of these dark matter particles going right through the Earth, but every now and then one of them will bounce off the nucleus of germanium and heat the whole thing up by 1/1000th of a degree. So that's all you have to do. build these detectors. And there are detectors like this all around the world right now looking for this stuff. But the important stuff, and when we discover it, well, we might understand the identity of dark matter. Actually, it's even more exciting because this dark matter was left over from the beginning of time, created in the Big Bang. But there's another place to look for it, and that is to recreate the conditions of the Big Bang. Are we okay? Yeah. Okay? Okay, good. To recreate the conditions of the Big Bang, or at least the very early universe, and we can do that. We can do that in a very small region, not too far away from here at the Large Hadron Collider in Geneva. And so there's a race, you see, because people in the Large Hadron Collider are hoping to produce the particles that are indeed dark matter and detect them there, and then the people building those detectors underground are hoping to detect the ones left over from the beginning of time, and there's a big race to see who will do it first, or whether either set of people will do it first, and it'll be very exciting. But the important point is we don't have to know what it is. This allows us to measure how much stuff there is in the universe. We can weigh clusters, and if we can weigh clusters, we've weighed everything. And we finally have the answer to how much stuff there is in the universe. And here's the answer with the drum roll. I can see people fainting in the back of the room. Physicists, in order to appear scholarly, when they measure something, they give it a Greek letter. And this Greek letter is omega. And omega is the ratio of the actual amount of matter in the universe divided by the amount of matter you need to make an exactly flat universe. So if omega is bigger than 1, the universe is closed. If omega is less than 1, the universe is open. And if it's equal to 1, the universe is flat. And you can see with great accuracy, essentially, we now know definitively, after 80 years of trying, we've been able to measure that, in fact, there's only 30% of the amount of matter needed to make the universe flat. The universe appears to be open. End of story. But there's a problem with that story. That is that theoretical physicists like me knew it was wrong. Because we knew the answer. We always know the answer. We're very rarely right, but we always know the answer. And we knew the universe was flat. We knew it was flat for many reasons. First of all, a flat universe is the only mathematically beautiful universe. And for other reasons that I'll tell you about in a bit, we're quite convinced it was flat. But here these damn observers were once again getting it wrong, as they usually do. But there's a loophole in this picture. Because, after all, you are only measuring matter that's in and around galaxies. Wouldn't it be better, and then from that, you're using Einstein's general theory of relativity to infer the curvature of the universe. Wouldn't it be better to measure the curvature of the universe directly? And amazingly, in the last decade, we've been able to do that. And I want to tell you a little bit about it. In these two-dimensional images, even though they're just allegories to the real three-dimensional universe, you notice something. If I draw a triangle on a flat piece of paper, I know what the sum of the angles are. And if I ask a British high school student, they'd be able to tell me it was 180 degrees. If I asked an American high school student, they would stare at me. But in a closed universe or an open universe, the number is different because triangles are different. It turns out because straight lines curve on a curved surface. On a closed universe, the sum of the angles is more than 180 degrees. In an open universe, it's less. It turns out that is exactly true even for a curved three-dimensional universe. So if we can measure a big enough triangle, we'd be able to measure the curvature of the universe. And in the last decade, we've been able to do that. And here's how we get this triangle. This is an image of the cosmic microwave background radiation, the afterglow of the Big Bang. It's radiation that's been coming to us from the beginning of time. It's actually coming to us from a surface that was produced about 100,000 years after the Big Bang. Because at early times, the universe was very hot. And when it had a temperature above 3,000 degrees, hydrogen, which is the dominant stuff in the universe, gets broken apart. Its protons and electrons get broken apart and separated. And so you don't have neutral matter anymore. You have what's called a plasma. And a plasma is opaque to radiation. You can't see through a plasma. So if we try and look out, we can't see past that point. It's like looking out the walls in this room. We're trying to see the audience. you work the picture forward, in early times the universe was opaque, 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 until the time the universe cooled down below 3,000 degrees, and then neutral matter, protons captured electrons, matter became neutral, and neutral matter is transparent to radiation. So if we look out, we should be able to see all the way back to that surface, just like I can see all the way back to this wall. That radiation that's coming from that surface in all directions, surface located almost a little over 13 billion light years away in all directions, that radiation coming at me has cooled as the universe has expanded. It was 3,000 degrees. It's now 3 degrees above absolute zero, and the radiation is in the microwave band. And that radiation was discovered by accident in New Jersey, of all places, by two people who didn't know what the hell they were doing. But they won the Nobel Prize anyway, because you don't have to know what you're doing to win the Nobel Prize. You just have to do it. And they did it. It was an important discovery. Now, this means if we image that radiation, we can get a picture of what the universe looked like when it was 100,000 years old. A picture from a surface located 13 billion more or so more than 13 billion light years away. And this is this image. This particular image was taken with this experiment. This is called the boomerang experiment. It's on a balloon, and it's a microwave radiometer. And it was put in Antarctica, and it was sent around the world, which is, of course, easy to do in Antarctica. At the South Pole, you do this. It wasn't quite at the South Pole. It took 2 weeks to get around. Came back to where it began, what is called the boomerang experiment. And it imaged the microwave background. Here's the image. This is an amazing image. Images like this actually won another Nobel Prize, because they're baby pictures of the universe. And this is a false color image. These are hot spots and cold spots in the microwave background. What they reflect is small lumps present at the beginning of time. Small by meaning small in variation. The lumps are actually huge, much bigger than the scale, in fact, is bigger than clusters. But these would be the lumps that would later collapse to form all of the galaxies and stars and planets and aliens and everything in the universe. So it really is a baby picture. These were the lumps that were created at the beginning of time. And I'll come back to it. But for our purposes, they're very important, because you see, it turns out gravity travels at the speed of light. So, lumps, if the universe is 100,000 years old at the time this picture was taken, then lumps that are bigger than 100,000 light years across don't even know they're lumps, because gravity can't travel across them. So they don't know to collapse. It's like in my country there was I think you get it here, there was a cartoon program called Roadrunner. And Wile E. Coyote always runs over a cliff and hangs around for a while before he realizes he's supposed to fall. And that's exactly the way it is for these lumps. Because lumps larger than 100,000 light years across don't know to collapse. So the largest lumps that can collapse significantly are 100,000 light years across. But that gives us a ruler. It's a ruler of a known length, 100,000 light years across, and a known distance. And I would love to stand out here, but I don't know if they can hear me. So I'm stuck behind here. And that gives us a triangle. We ask, how big does a ruler look on that surface? And as the light rays travel in straight lines, the ruler should look about 1 degree across. If the light rays curve inward, as they would do in a curved universe, the ruler will look bigger, maybe 2 degrees across. And if the light rays curve outward, as they do in an open universe, the ruler will look smaller, half a degree. So a picture's worth 1,000 words. So here's a different false color image of that same region. And here are some universes made on a computer. A closed, flat, and open universe, and we just randomly generate lumps and ask how big should a 100,000 light year across lump look in such a universe. Well, it would look that big. But this lump is bigger than these lumps. And in an open universe, how big should the average 100,000 light year across lump? It should be one of these little things. But these are smaller than these lumps. But just like Goldilocks, in a flat universe, it's just right. In fact, it's right now, we know, to an accuracy of better than 1%. We have proved that the universe is flat. Just as we thought. So we do this. But there's a problem. There's a problem. I just proved to you 10 minutes ago that the universe was open. There's only 30% of the amount of stuff needed to make the universe flat. So we're missing 70% of the stuff. Well, we measure all the stuff around galaxies. So if this energy is somewhere. It can't be around galaxies. That has to be where galaxies aren't. What is where galaxies aren't? Nothing. Now it turns out, if you put energy into nothing, which is allowed in general relativity in principle, then it has a very interesting property. All other sorts of energy are gravitationally attractive. But if I put energy into nothing, it's gravitationally repulsive. So if I were looking at the expansion of the universe, and this is a way we determine the expansion of the universe, measuring velocity as a function of distance, for reasons again I won't go into. If I filled up empty space with energy, the universe would accelerate, it would speed up because of that repulsion. A sense of the universe would slow down. Well, in 1998, two groups of astronomers who didn't know what the hell they were doing tried to measure the rate at which the universe was slowing down. And this became the cover of Science magazine again. Now, we're trying to measure the rate at which this curve is curving downward. Measuring these objects called supernovae at large distances. Now, to guide the eye, what I want to do is draw a straight line through this data set down here and make the whole thing horizontal. And if the universe was slowing down as a sensible universe should do, these distant objects called supernovae, exploding stars, would follow that curve. But they don't. They're not even below the straight line. They're above the straight line. What does that mean? One of two things. Either the data's wrong, which is usually the case in astronomy, or the universe is accelerating, speeding up. Now, just for fun, we can ask how much energy would I have to add to empty space to fit that data. And the amount I have to add is exactly what we're missing. If I put 70% of the energy of a flat universe into empty space, everything works. So, how can that be? Well, it turns out that empty space isn't so simple. I mean, if you ask a 4-year-old what's the energy of empty space, they'd say nothing because there's nothing there. But that 4-year-old hasn't taken quantum mechanics. Well, at least in the United States. And quantum mechanics tells us that empty space is really a boiling, bubbling brew of virtual particles popping in and out of existence at a time scale so short you can't measure it. And in fact, that sounds like philosophy. Forgive me. Sounds like counting angels on the head of a pin. Maybe theology. But it's not. Because while we can't measure those virtual particles directly, as they're called, we can measure them indirectly. This is actually an image that was shown at the Nobel Prize ceremonies in 2004. And here, this is actually a picture, or an animation, but it's one derived from mathematics, of what the empty space inside of a proton looks like. This is using the theory that was developed that allowed you to calculate this, which won the Nobel Prize. And it turns out that these fluctuating fields and particles that are popping in and out of existence are actually responsible for most of your mass. 90% of the mass of a proton doesn't come from the quarks that are inside of it. You may have learned in high school that protons are made of 3 quarks. Only 10% of the mass of the proton comes from that. 90% comes from this stuff. So, if we can the theory tells us how to calculate that, if we can calculate the contribution of these virtual particles to the energy of a proton, we should be able to calculate the contribution of the virtual particles to the energy of empty space outside of protons. When we do, we come up with the worst prediction in all of physics. We calculate that the energy of empty space should be roughly a gazillion times the energy of everything we see. And as I say, this is literally the worst prediction in all of physics, which is why we never talk about it. We calculate that the energy of empty space should be at least 120 orders of magnitude times the mass of everything we see. And that's impossible, because if that was the case, nothing would have ever formed. And this was so problematic that, in fact, in order to sleep at night, we theorists knew the answer. The answer was 0. Because it turns out, we didn't know how to cancel a big number and leave a non-zero number in the 121st decimal place. But 0 is a nice number. We can do mathematical symmetries produce 0 all the time, so we figured there was some new symmetry of nature and the problem would be solved and everything would be okay. But in fact, we've learned that that's not the case. Empty space has energy. It's 120 orders of magnitude smaller than we would predict, and we don't have the slightest understanding of why. Not the slightest. So, this is the universe in which we live, and it allows me to set the stage for asking the question, could it have come from nothing, and where is it going? So, to summarize what I've taught you so far, the dominant energy of the universe resides in empty space. We don't have the slightest idea why it's there. And if anyone comes to a lecture hall, and there's still people in who can hear and not outside, there's a video room out there, and they try and explain, they claim they know the answer, they're lying. Okay, especially if they're a string theorist. We don't understand it. But we think its existence is probably tied to the beginning of time, and it will determine our future, as I'll get to. So, that's it. Let me summarize. The first very important thing I want to tell you all, especially the people in the overflow room, is you're far more insignificant than you thought. But you too. Not me, but all of you. Because, we got a problem? Okay, you just coming out to say hi? Oh, I'll repeat the questions for you again. I'm not there yet. Okay, good. Thank you for anticipating. Okay. I know I was going somewhere. Okay, let's see. So, you're insignificant. That's the important point. You are far more insignificant than you thought, because in fact, that picture I showed you of all the stars, you can get rid of us and everything we can see in the night sky, all the stars and galaxies, and the universe will be largely the same. We are a 1% bit of pollution in a universe full of dark matter and dark energy. So much for a universe made for us. We are an irrelevant sideshow. Get used to it. Okay, now, I want to talk about this question of how the universe will end, because it leads to this interest in why theorists like me knew the universe was flat. So I want to take you back to a wonderful time for all of you. I want to take you back to high school physics class. And we teach our physics students, say I take up this pen and I want to throw it up in the air, it comes back down. Okay? I throw it up higher and it comes back down. If I throw it up really high, there's no ceiling, it doesn't come down at all. And so if I throw out the escape velocity from the Earth, it leaves the Earth. And we actually teach physics students how to calculate it. And I just want to remind you of that. I'm sure you all know this, but I want to remind you, you may have once learned. When we throw a ball up, or a coin, or a pen, it has energy. And those energy comes in two pieces. A positive piece, which we call the kinetic energy, related to the motion, and a negative piece that comes from the gravitational attraction of the Earth. And it turns out all of this just becomes simple bookkeeping. If the total energy is greater than zero, if the positive piece beats the negative piece, then the coin will escape. So if I make the positive piece, the velocity big enough, it'll beat the negative piece. If the velocity isn't big enough, so the negative piece wins out, it'll return. And that's how we calculate the escape velocity from the Earth. Well, it turns out the same thing is true for the universe. If our universe is expanding, and here's a small region of our universe, and these are galaxies, not sperm. And we're here. If we look out, and we're looking at galaxies, they're all moving away from us on average. That's what Mr. Hubble discovered. Now, if the universe is the same everywhere, we don't have to calculate what happens to all galaxies. We just have to calculate what happens to one galaxy, and the same thing will happen to all the rest of them. So I'll pick a galaxy, and it's moving away from us. So to calculate what will happen to it, I just calculate the positive piece of its motion, which comes from its velocity, which happens to be related to the expansion rate of the universe that Mr. Hubble measured. And then to get the negative piece, I have to know all the mass that's pulling it inward. Well, that means I measure the total amount of stuff in the universe. The density of stuff pulling it inward. And it turns out, therefore, if the negative piece beats the positive piece, or B over A is bigger than 1, that galaxy will stop and come back if matter is all there is. If B over A is less than 1, so the positive piece beats the negative piece, the galaxy will go on expanding forever. Okay? But what is really neat and remarkable is that this ratio, B over A, is nothing other than this quantity omega, which tells us about the curvature of the universe. And we measure omega, it's exactly equal to 1. We live in a flat universe. What does that mean? That means B is exactly equal to A. What does that mean? The positive piece is exactly equal to the negative piece. What does that mean? The total gravitational energy of every object in the universe is 0. Now, if you were going to create a universe from nothing, what would you make the total gravitational energy? It's the first hint that perhaps we can have our cake and eat it too. So I want to spend the rest of the time here talking about how the universe can come from nothing. And essentially to discuss the important fact that we can't prove our universe came from nothing. But amazingly, the characteristics of our universe are precisely those characteristics we would expect of a universe that came from nothing, was created by the laws of physics without any supernatural garbage. Okay? So, this is what I've already just said. A flat universe is the only one where the gravitational energy of every object is 0. So this leads us to begin to talk about nothing. But when we talk about nothing, we have to be a little more precise, I have learned, because people get upset by the idea of nothing. I would argue, and I still argue, in spite of many people who argue the contrary, that nothing is a physical quantity, not a philosophical quantity. Because something is a physical quantity. And so in order to understand nothing, we have to understand something. And the point is, science has changed our understanding of both. So the first answer to the question, why is there something rather than nothing? And by the way, that question is really, how is there something rather than nothing? Because the why question is unimportant. Why is there something, but I use the why question because I'm stuck in the jargon of the time. Why is there something rather than nothing? The simple answer is, because nothing is unstable. The surprising thing would not be that there's something, but rather that there's nothing. But then, of course, it would be around to ask the question. Because it turns out, because of those particles popping in and out of empty space, once I add gravity into the mix, so I can create particle-antiparticle pairs that have 0 total energy, because of their gravitational attraction, they can persist forever. So if I have no particles to begin with, and just empty space, the nothing of the Bible, if you wish, an eternal empty void, and I wait long enough, quantum mechanics guarantees me particles will be produced. They'll spout out of nothing due to the laws of quantum mechanics. So it's very simple. Nothing is unstable. You wouldn't expect to see nothing. You'd be very surprised if there were nothing. Okay. Now that, however, does not satisfy many people. Well, because it gets rid of God, for the first part, but also because, well, it doesn't really look like nothing. After all, even though there's nothing there, and there is nothing there in empty space which weighs up, those particles aren't real. There's nothing there. You could, from now to eternity, try and see what's in there, and you'd see nothing. Okay? So it really is nothing in that sense. But nevertheless, space is there. So this is, but before I get there, let me just summarize. I forgot I wrote it down. So, if you have empty space, you can create real particles with 0 total energy, and you can do it without any you don't need God. You don't need some outside intervener. The universe can do it all by itself. Okay? Or the nothingness of the universe. But, as I point out, that doesn't seem like it's nothing, because although I don't have particles and I don't have radiation, I've got space. Where the hell did the space come from? You might ask, especially if you don't like this answer. And then the answer to the second question is very simply, gravity, Einstein's general relativity, is a theory of space and time. If I make general relativity a quantum theory, and we can't yet, we don't have a theory for quantum gravity, but we have some ideas, good ones and bad ones. But whatever theory of quantum gravity ultimately exists will make space and time quantum variables. And quantum variables fluctuate. That's what causes virtual particles to pop in and out of existence in empty space. That, in fact, as I'll describe, is what we think cause those lumps that eventually created us and everything we can see, quantum mechanics. We are here as a direct result of quantum mechanics. But if I make space and time quantum mechanical at the very beginning of time, then quantum mechanics will allow space to be created, universes to be created where none existed before. Space and time themselves can fluctuate into existence and fluctuate out of existence. I can create universes and spaces where there was literally no space or time before. Most of them will disappear in an instant, just like our virtual particles. But if I create a universe that has zero total energy, that universe can persist forever. Now, it all sounds great because I just told you in a flat universe, every object has zero gravitational energy. So it would really be nice if that was the end of the story. But it's not. I gotta be honest. It turns out we can't calculate the total energy of a flat universe. The gravitational energy of every object in a flat universe is zero. But Einstein told us E equals mc squared. So objects have rest mass and they have energy. Okay? And it turns out the only universe for which I can calculate the total energy and find out it's precisely zero is a closed universe. A finite closed universe. That's not the universe in which we live. Well, that's true. But most closed universes will collapse. Remember I told you they collapse? In an instant, in a microsecond. The only kind of closed universe that could survive long enough for us to be around to ask the question is one in which, for a little while, there's an energy in empty space. That energy in empty space is gravitationally repulsive, and it'll puff up that closed universe to be a very large scale. And that is exactly what particle physics predicts should have happened in the early period of our universe. It's a phenomenon called inflation. Good thing to talk about at the London School of Economics. But this is inflation we understand. Particle physics says at early times, I don't know if I have, I'm wondering if I have a picture. Yeah. Okay, I'm going to talk about this. I'm going to talk about beer. I grew up in Canada, so it was about beer. If any of you, the little children shouldn't listen to this. If any of you have ever had a party and you bought some beer and you forgot to put it in the fridge, what do? Well, you do what I do, you put it in the freezer, right? And then you forget about it. Then what happens? Well, you open it up and suddenly crash! The bottle breaks and the beer suddenly freezes. Why? Because under high pressure the beer was liquid. But the minute I opened it up, the beer changed state. It froze. And when it was liquid, it was called a metastable state. And when I opened the top, it could release energy and break open the beer bottles. Our picture of the early universe is precisely that. That as the universe was cooling down, it got stuck in a metastable state, where empty space had energy stuck in it, large amounts of energy, causing the universe to expand by a huge amount, a factor of 10 to the 90th in volume in a time period of a millionth of a billionth of a billionth of a billionth of a second. It sounds impossible. It sounds crazy. But it's predicted by the theory. Moreover, it turns out during that period, we can calculate what will happen. And it turns out quantum mechanics will produce fluctuations which get puffed up and made very big and get frozen at early times and get turned into density fluctuations that might one day collapse and form galaxies. And if we ask what would that distribution of fluctuations look like, it would look just like the picture I showed you in the cosmic microwave background. That gives us great confidence, in fact, that this picture is probably true. And you are here literally because you're resulting from quantum fluctuations. But from the point of what I want to talk about, go back to what I said before. And by the way, that phenomenon is precisely the kind of phenomena that now has greater validity because we may have discovered the Higgs particle at the Large Hadron Collider. The Higgs particle also tells us that there's some uniform background field throughout the universe, called the Higgs field. But this idea of inflation requires a different field that gets stuck in a uniform phase in the early universe, and it was very slimy, that prediction, because we didn't know of any fundamental scalar fields that should exist. But now we seem to know of at least one. So this picture has gained currency. The picture of inflation is now much more believable with that beer. So if there's a period of inflation, it'll puff the universe up, but just like if I blow a balloon up and make it very big, say the circumference of the Earth, it looks flat. The Earth looks flat in Kansas. And so our universe, the only kind of universe that could survive, closed universe that could have been created by quantum gravity, that would survive long enough to survive to the present time, is a universe that looks flat. precisely like the one we live in. So, no space, no matter, no radiation, no space. You can all come from a quantum fluctuation, and it will look precisely like the universe we live in. Some people say, however, okay, well that's okay, you got no space, no matter, no radiation, but what about the laws? What about the laws? Who created the laws? And the interesting thing, although it's depressing, is even the laws of physics themselves may be accidental. And the reason for that is this weird energy of empty space that we don't understand.